all, maybe I'll start this talk with emphasizing that the move to green renewable energy is accelerating very rapidly. And so if in 2016, people forecasted that by 2040, there will be 35% of electric vehicles on the road among passenger cars, last year, the prediction rose to 58%. And now, after the war in Europe, this transition is going to be greatly accelerated. Germany now set a new target for 2035 to move to 100% renewable energy. And it makes sense because of this very high prices for gasoline, for oil and gas. And so, what are the important considerations? If you move to renewable energy, you have to store this energy. If you have an electric car, you have to have a battery. If you have a grid energy, you have to store energy as well. And lithium-ion batteries became the backbone of this energy transformation. But there are many factors that are important for lithium-ion batteries, and the current materials do not satisfy them. The minerals that you use in lithium-ion batteries, they have to be abundant if you want to transition the whole economy to green renewable energy. And the batteries have to be of low cost. They have to offer safety. And for automotive applications, they also need to be able to charge faster and provide high energy density so you can have a longer driving range in cars. And materials that go inside the battery define all the key battery specs. Now, to move to new material chemistries is challenging, and to maybe put things into perspective, I want to emphasize that in the history of humankind, there have been only 4 commercially successful rechargeable battery chemistries: lead acid, nickel cadmium, needle metal hydride, and intercalation type lithium-ion. And each of these materials innovation led to lighter batteries, so they gain higher specific energy, and led to smaller batteries, so they gain higher energy density. And now we are living in a very special time because we see the emergence of the 5th type of the batteries, conversion type lithium-ion, which will make energy density characteristics even higher, while at the same time reducing the cost. There are many other concerns with conventional materials used in lithium-ion batteries, especially in automotive battery specs. They all rely on the use of relatively expensive metals. And those metals are not present in large quantity in Earth crust. And so there are multiple supply chain limitations. So if you analyze all the kind of resources of, for example, cobalt and all batteries that you use in your cars and your cell phones, laptops, majority of those are comprising cobalt. And so if you look at the demand for the cobalt and the supply of cobalt, you will see that there will be significant shortage. And we predicted it quite some time ago, the shortage within 10 years or so. And now because of the war in Europe, there is even more limitations, and we see significant price increase for both cobalt and nickel. So you need even more nickel for lithium-ion batteries. And again, even though the amount of nickel in the world is significantly larger, we expect a significant shortage, and as a result, increase in prices in 2018. And now the price for nickel almost tripled. So how do we overcome these challenges? Well, one of the ways, as I mentioned, is to move to the so-called conversion type chemistries. And you can evaluate performance of these batteries with conversion type chemistries considering the building block, the cathode, the anode separator, the current collector foils, and estimating the energy density or specific energy of this unit stack. And you can estimate that if you move to these conversion chemistries, for example, silicon-based anode materials and conversion type cathodes like lithium sulfide, metal fluoride, you can increase energy density. And for many applications, for example, for flying cars, for electric planes, for even trucking on the road, the weight of the battery is also very important. And so if you move to this conversion type chemistries, you can also reduce the weight by over 3 times. In addition to silicon, all these materials that are considered to be the most promising for conversion type chemistries are quite abundant and relatively inexpensive. For example, sulfur, iron, silicon are incredibly inexpensive materials. So we made some predictions on the future prices for lithium-ion batteries, considering multiple relatively conservative assumptions in our model. And so we predicted that by moving to silicon chemistry, and we assume, let's say by 2030, the price for high-performance lithium-ion batteries will be reduced below $75 per kilowatt hour. And now I think that these predictions are even conservative. And this is because there are multiple components that contribute to the pricing. There is manufacturing of lithium-ion batteries, there is inactive cost of inactive materials such as casing, electrolyte, separator, foils, and then there is also the prices of the active materials, cathodes and anodes. And if you look in the past, you will see that, yes, there are multiple chemistries in the batteries. They have different energy storage characteristics, they have different sizes. But typically, if you go to higher performance batteries, batteries that can store more energy, the price becomes smaller, not larger. And this is because, let's say, to produce a battery for a car, for electric vehicle, you would need to make fewer cells of the same size if these cells store more energy. And so in the future, the price are going to keep reducing. The cost of manufacturing is steadily reducing. The cost of raw materials is less so. So you can have different predictions for the batteries if they still rely on nickel and cobalt. But if you move to conversion type chemistries fully, to move to silicon-based anode, move to sulfur-based or metal fluoride cathodes, the price for lithium-ion batteries will be below $40 per kilowatt hour. And this is an excellent news because it means that high-performance, clean, renewable energy-based electric vehicles are going to be much less expensive compared to combustion engine cars that we see on the road today. So this transition to renewable energy and this transition to electric vehicles is inevitable, which is fantastic. Now, silicon anode is the most significant milestone. It offers about 10 times higher gravimetric capacity compared to incumbent graphite currently used in your batteries that you have in the cell phones and cars. It offers about 3 times higher volumetric capacity. At the cell level, it gives you up to 40%, maybe even more energy boost. And silicon is a widely available global commodity precursor. There is as much silicon in Earth's crust as all other metals and semi-metals combined. So very attractive. In the meantime, it's also very challenging to work with. If you use relatively large particles, conventional size particles, they tend to pulverize during storage of lithium. They also swell a lot by 300% when you lithiate it. And these volume changes during lithiation and delithiation induce electrolyte decomposition. So typically, the lithium-ion battery operates in the regime when the anode is at the potential when electrolyte is not electrochemically stable. It's going to be reduced chemically or electrochemically. And so, and it forms typically so-called solid electrolyte interface layer, ACI. And if the particles change volume very small, then this ACI can be quite stable. But if the volume changes are significant, the ACI continuously is breaking, and you induce continuous electrolyte decomposition, continuous consumption of lithium, degradation of the batteries, increase of battery resistance, and so forth. In the meantime, when I joined Georgia Tech over a decade ago, we saw that multiple of these challenges could be overcome with smart materials engineering. So for example, if you move to smaller particles, you can stabilize mechanical issues with this chemistry. Unfortunately, small particles also have very high surface area and still suffer from electrochemical instabilities. We also learned that if you form composite materials, you can dramatically reduce swelling of volume changes at the particle level. And finally, if you figure out how to produce particles with stable dimensions and sufficient porosity and that volume changes in silicon, then you can also stabilize the ACI or stabilize the electrolyte decomposition, prevent electrolyte decomposition. And so in 2011, I co-founded the company Seal Nanotechnologies with two amazing co-founders with entrepreneurial expertise in hardware technologies. And so we steadily grew the team from the small incubator at Georgia Tech to now well over 300 people working at Sila. We currently occupy 3 buildings, around 100,000 square feet, and I recently purchased a much larger manufacturing site to produce materials to power up to 1 million electric vehicles per year. So when we started the company, we set the product vision. We wanted to make sure that our product would be completely compatible with existing and expected future lithium-ion battery factories. So it should be drop-in. So the particles should be medium size, micron scale, exhibit small volume changes at the particle level in spite of very large volume changes on silicon. And it was also very important for us to be able to produce it economically at global scale, which means using low-cost commodity precursors and large volumetric manufacturing technique. And so of course, it's easier said than done. And so we had to innovate at multiple levels to be able to produce these particles and also to scale up the production. So as you know, in electronic devices, you can operate them very stably, effectively for millions, sometimes billions of cycles. But batteries typically degrade much faster. And this is because in electronic devices, the electrons move, but atoms, they commonly stay put. In lithium-ion batteries, the lithium ions, they move back and forth between the anode and the cathode. And this motion induces a lot of challenges. Now, if you move to this new chemistry from so-called intercalation to conversion chemistry, now every single active atom of material, so an atom of active material moves during each charge and discharge. It breaks and restores chemical bonding. And so obviously it's much more challenging. Effectively, you have a chemical reaction at the particle level. And so we had to borrow different steps from multiple industries. We also had to develop very high precision reactors at very early stages to be able to tune material properties and see the signal much more clearly, because sometimes the signal is very small. And what we also learned that new material innovations often require new metrology. So we develop our unique characterization tools that we use in our reactors, that we use at the battery level. And that's where, combination of amazing science, material science, but also many other disciplines, as well as high performance engineering was so critical for our success. In many cases, when we do research in academia, we focus on one particular phenomena. We want to demonstrate a particular change, phenomena, or let's say breakthrough in one particular direction, but often at the expense of many other criteria. In industry, you have to satisfy like 20 different criteria to make a successful product. And so we had to develop, again, new tools, unique tools to monitor even tiny changes in volume of the lithium-ion batteries during operation in situ. You have to make sure that industry also changed when we were developing this product. It moved to slurries comprising organic solvents to water-based slurries. So we had to adapt our materials to new reality. We also had to satisfy multiple safety tests that people sometimes don't realize may be feasible with certain solutions that they offer in academia. So you have to expose your cell to high voltage at high temperature. It has to produce very small gassing. It has to retain very high capacity and so forth. There should be no end-of-life gassing. So when your battery degrades down to zero, it shouldn't explode. It should offer long calendar life. And if in electronic devices, you want the batteries to last at least 4 to 5 years, for electric vehicles, the calendar life of the batteries should be in excess of 10 years, preferably in excess of 20 years. So much more challenging. And so we had a pilot plant operating, producing materials 24/7 with very high yield for over 3 years. We now having a larger factory producing materials in Alameda, California, and again, as I mentioned, building much larger facilities elsewhere. And so, in 2017, we demonstrated, very high performance, which now exceeded these values. I am allowed to share only these graphs at the moment. And so the capacity of our composite materials now is about 5 to 6 times higher compared to the graphite on the gravimetric basis. And again, we have to produce real high aerial loading cells for automotive and electronic device customers. And all the scientific breakthroughs and performance climbs only matter when you see them in real products. And so last year, WOOP 4.0 launched a revolutionary product enabled by Sila Science. So when we incorporated our technology to enable smaller, better performance batteries, which again enabled important features in a much smaller, much more elegant size. And so again, if you don't have it, I highly recommend WOOP 4.0. It's a remarkable fitness tracker. We also built partnership with automotive producers. We publicly announced partnership with Mercedes-Benz and BMW, and these companies are going to build amazing electric cars and are going to introduce state-of-the-art Sila-enabled technologies in their batteries. Now, there are multiple positive impacts, of course, to end customer, but in addition to that, at the factories. So if you introduce our technology, our materials technology, without any changes in equipment, you can increase the output, right? So there is no additional expenses. And so if the battery, for example, factory supplied batteries for, let's say, 1 million electric vehicles, with our technology, they can supply in 1.2 million electric vehicles, so 1.3 million electric vehicles per year. So you have reduced depreciation, but you also reduce CO2 emission during production. Now, once you develop and scale up the anode product, then the next step is to develop conversion type cathode materials. And one of those promising candidates is sulfur-based lithium sulfide. And sulfur, as you know, is low cost and abundant, enables you to achieve significant weight savings for the batteries, but also exhibits very poor performance. It degrades rapidly. It suffers from very high losses. It's very sensitive to environment. You can't process it in conventional factories. And so in many cases, you have to figure out how to produce hierarchical composite particles to overcome some of these challenges. And this is one of the examples of the publications we published at Georgia Tech in 2015, again, overcoming some of these challenges. So making composite particles, small dimensions, with this core-shell architecture, when small nanoparticles of active material, in this case, lithium sulfides, are embedded in this amorphous matrix. And typically, conversion materials degrade much faster, especially if you go to elevated temperatures. They typically exhibit much larger voltage hysteresis or energy losses during charge and discharge. And they demonstrated that, yes, all this degradation can be overcome, it can be dramatically reduced. You can have very stable performance for hundreds of cycles, in this case 600 cycles, demonstrated at Georgia Tech, and again have very small voltage hysteresis during charge and discharge. Metal fluorides, and again another very interesting material, even more challenging compared to lithium sulfide, and again similarly would likely require nanostructure and shell protection in order to perform adequately in real cells in real life. Even though some metals are more expensive, but iron is very inexpensive, very low cost metal. In addition, in many cases, you can use waste of metallurgical industry as a precursor for this new cathode chemistries. And similarly, we demonstrated quite some time ago that by nanostructuring this material, nano-confining it within this matrix, in this case, activate carbon matrix, amorphous carbon matrix, you can achieve significant performance boost. You can achieve longer cycle life. You can get 2 to 3 times higher gravimetric capacity compared to state-of-the-art materials. In many cases, when the performance is good at low temperature or room temperature, the performance suffers much greater at elevated temperatures. So, for example, when you heat the cells operating with metal fluoride cathodes at high temperatures, typically degradation is accelerated. You have massive degradation of electrolyte, you have significant degradation, dissolution of active material. And these issues and others sometimes may be overcome if you figure out how to stabilize the ACI, how to stabilize nanocomposite particles to avoid direct contact between electrolyte and active material, or if you use solid-state electrolytes. Could be polymer-based, would be ceramic solid-state electrolytes. Now, in addition to enabling these new materials, this solid-state chemistry may, in principle, give you significantly better safety, right? If you have electric vehicles, if you have a Tesla or some other high-performance electric vehicle, the batteries don't use solid electrolytes. They use conventional organic electrolytes. Even though they're not perfectly safe, they're safe enough. So if your car gets on fire, typically you have 10, 20, sometimes 30 minutes to stop, leave the vehicle to make sure that you're safe. In the meantime, if you use, let's say, electric engine on a boat or on a plane, if you have electric plane, you don't always have time to land safely, right? So the batteries for these applications have to be done with extreme safety measures in mind. Unfortunately, at the moment, all the solid-state electrolytes that have currently been considered is heavy. It's also very expensive to process. So you move to solid state, you suffer from larger weight, higher weight, and significantly higher cost of production. And so we did some interesting battery innovations at Georgia Tech when we develop electrolytes that have very low melting point. And we can heat the cells at relatively moderate temperatures, a few hundred C, and then infiltrate electrolyte in a liquid state as conventionally done. And then as the battery cools down, it solidifies and produces solid-state battery. So in this case, the production of batteries can be done using conventional equipment already available at all these facilities. And so we demonstrated this work on two exemplary electrolytes, anti-perovskite electrolyte and lithium borohydride-based electrolyte, but there are many others in development. And so we use both conventional materials such as nickel, lithium nickel, cobalt manganese oxide, NCM material, again used in majority of electric vehicles, but we also use conversion type materials such as lithium sulfide on the cathode, and then on the anode we use either graphite or LCO. And with melt infiltration, you can achieve perfect wetting, perfect contact between the particles. Again, very high density of the particles packing in electrodes, and very small fraction of inactive material or electrolyte. And because of the low melting point, again, there are no side reactions or minimum side reactions between active material and electrolyte, which again is very critical for fabrication. And you can achieve high capacity of intercalation materials, small hysteresis, good performance. But we also demonstrated that this technology can be applied to conversion chemistries, lithium sulfide, and demonstrated in this case almost 1,000 stable cycles for this particular chemistry. Again, I think it's very exciting technology, and it's likely going to be used in the future. So in summary, I want to emphasize that unfortunately, conventional intercalation type lithium-ion batteries are reaching their performance limits. And so there is an importance to move to new materials, new chemistries, to overcome supply limitations, to reduce costs substantially. And I think this, with new materials, lithium-ion batteries can dramatically enhance our transition to renewable energy. And this requires for us to explore, develop, and scale these new chemistries at a massive global scale to have a large impact. We have proven silicon anodes to be commercially viable, and again, the scale-up is in process. Others will follow. And solid-state technology, which look attractive for some applications, I think needs to be compatible with lithium-ion battery manufacturing to have a fair chance to compete with liquid organic electrolyte. Thank you so much for your attention. With this, I would like to thank you, and I wanted to budget some time for questions.
Once again, I'll pass the microphone around for questions. Here we go.
Thanks for your talk. Seth Burbano from Murata. For the melt infiltration part, do you need to do some vacuum to backfill into the porous structure, or?
Yeah, the same way you do with conventional electrolytes, you typically fill it under vacuum. We didn't use vacuum filling, but you'd have to use it in industry.
Thank you.
Additional questions? Gleb, with the growth of your company, do you see expanding into Europe that is suddenly driving these purchases of batteries? You're going to stay US based?
So all the large manufacturing of materials are going to be US based initially, but eventually we have to expand globally. There are no companies supplying, producing some materials for global supply that don't have factories in all continents. You have to do it. And especially nowadays, with all the events in the world, I think we did a little bit too much in globalization. I think you have to have local production of the key materials on all continents. So in Europe, you have to have them in Asia, but you also have to have them in the US.
Well, I was watching the Masters this weekend and saw the EQ advertised over and over again. So congratulations on getting involved in that very nice vehicle.
Thank you.
Any further questions? Well, with that, let's thank Gleb.
Thank you.